In the fourth lecture of the limit series, we will talk about infinity. Infinity is a difficult concept for a lot of high school students and college students and grad students and professional mathematicians as well. It's not a number, we have to remember that. And so, as it says on the screen, seeing infinity in a limit expression, it means something a bit different than the real number expressions we've been dealing with. If I say x approaches infinity, that can't really happen. Infinity is not a thing that can be approached. X approaches infinity means x is getting larger and larger without bound. And similarly, in a shorthand, I might say f of x becomes infinite. Well, it doesn't really become infinite. I just mean that it, again, becomes larger without bound. So always be careful when dealing with infinity. Okay, the first way we're going to use infinity is as a new way to describe horizontal asymptotes, and you've seen this in the previous lecture. If you see limit as x approaches infinity of f of x equals c, and c is a real number, then this means that for large enough values of the input to the function, the output will be close to c. How large is large enough? How close is arbitrarily close? Again, these things do have precise meaning. We can just take it to mean as close as you want it to be. In other words, y equals c is a horizontal asymptote on the right. Similarly, if x approaches minus infinity, it's a horizontal asymptote on the left. So already we can see the benefit of using the limit notation in case the end behavior is different on the left and the right. And that happens in a lot of your pre-calc functions, like e to the x has an asymptote, horizontal asymptote on only one side, and a function like arctan has a horizontal asymptote on both sides, but it's a different value on both sides. Remember, tangent inverse goes to minus pi over 2 as x becomes arbitrarily large negative number, and it goes to pi over 2 in the positive direction. And of course, many functions don't have a horizontal asymptote on either side, so what can we do in this situation? Well, if I write limit as x approaches infinity of f of x equals infinity, that means not only is there no horizontal asymptote, but the function will increase without bound. And of course, I could use a minus infinity in either place, and that would tell me the end behavior on the left, or it might tell me that the function decreases without bound. Now, you might say, although a function increases, different functions increase at different rates. And for example, the natural log increases very slowly, e to the x increases very quickly, y equals x squared increases faster than a line but slower than an exponential function. So it does leave a lot unsaid, and we might ask how fast does one function grow to another, given that they both approach infinity. This is actually a deep question, a good question, and one that we might have a more detailed answer for a little bit later on, perhaps in a more advanced course. So it's also possible to say that a limit does not exist. And technically, if you approach infinity, if f of x blows up to a large number, again, that limit doesn't really exist. But we're giving more information and saying it doesn't exist because the function increases without bound. So to write down a few of those examples that we've already mentioned, limit as x approaches minus infinity of e to the x equals 0, whereas limit as x approaches positive infinity of e to the x equals infinity. The tan inverse function approaches minus pi over 2 when x goes to minus infinity, but positive pi over 2 when x approaches positive infinity. For a rational function, we already know about the horizontal asymptotes. If the degree of the numerator is equal to the degree of the denominator, so cubed over cubed here, then the end behavior is a horizontal asymptote with a value equal to the ratio of the leading coefficients. So the limit as x approaches either positive or negative infinity of this rational function is 3/5. And again, it's the same in both directions. The limit of the sine function doesn't exist, and it's not infinity either. You know, it doesn't blow up to large values. It stays between 1 and -1, but it oscillates between those values in perpetuity. So we can't really say anything about the limit. I guess this would be true of almost any periodic function that's not a constant function. The limit would not exist because you have oscillations. The limit of, maybe there should be parentheses here, the limit of x minus 5 sine x does equal infinity, and despite the function is not exclusively increasing, you know, it increases, decreases, increases, decreases if you look at a graph, but it tends towards larger and larger values. So we can still say that the limit is infinite. It doesn't have to be increasing the whole time. Okay, so those are all what happens when x approaches infinity. A vertical asymptote is when the value of the function becomes unboundedly large. So if we have a limit equaling infinity where the input, where the function input, let me start again. If a limit equals infinity, we're describing a vertical asymptote. So as x approaches 0, 1 over x squared approaches larger and larger numbers, approaches infinity. I used 1 over x squared because that's positive on both sides, but I think, again, we saw in an earlier lecture, when you have a vertical asymptote, it often is positive on one side and negative on the other. So we will distinguish which side we are approaching from when we write down the limit expression. Here, if you think about the secant function, which, remember, secant is 1 over cosine, so it has an asymptote at pi over 2. Well, if we approach from the left, so we have a little minus sign here, if x is less than pi over 2, but close to pi over 2, secant x will be a large positive number. And the limit is positive infinity. However, if we approach from the right, so x is getting close to pi over 2, but is always bigger than, the plus lets us know that we are larger than the limit point, then the secant function is negative, and so the limit is minus infinity. And we'll have some precalc intuition which we can extend. In general, if you have two functions and f approaches 0 but g does not, then the quotient g divided by f will have a vertical asymptote wherever f approaches 0. Whenever that happens, you'll have to analyze the left and the right side of that asymptote and figure out if the function is positive or negative near that point.